Open this. Say good morning.
Good morning.
You want to greet all the distance guys in their pajamas watching this in their living room. So welcome to the fourth lecture. Today we're going to start building our stack of consumption and our stack of production. And the consumption stack starts with, what do you think is the worst thing? I'm thinking cars, transportation. So we're going to start building our stack. We're going to look at transport today. We're going to talk about cars, planes. We'll talk about freight later on. And in the right-hand stack, we're going to be putting the possible sources. And we're going to start with wind and solar. So we're going to look at how it turned out for the UK, which you already read. And then we're going to try to crunch some numbers from Ohio and see how we compare. First, if we're going to measure the energy used by a car, there's a number of places we could do it. We could measure it right here at the gas pump. How many gallons does it take me to get wherever I'm going? Or maybe I could take into account that somebody has to drive the gas from the refinery to the gas station, so that takes fuel and energy to do that. Or maybe I should take into account that we have this crude oil that we have to take to a refinery, the energy used to refine it, the energy used to transport the refined gas, etc., down to me. Or maybe I have to transport the crude oil from the well or the Gulf of Mexico, wherever, ship it to the refinery, more like that. Or maybe I should take into account that all this energy ultimately came from plankton and dinosaurs. Plankton, we'll say, much more plankton than dinosaurs. And so we can measure the energy that the plankton used to make all this other stuff happen. And this is a cute little icon here in the time. Oh, isn't that cute? Or really fundamentally, ultimately, all the energy comes from the sun. The only energy that we use that doesn't come from the sun ultimately would be geothermal energy. Well, nuclear energy. Okay? So, where should I measure the energy used by a car?
Shouldn't you have one more path in there too?
What?
The creation of the car.
Oh, good point. It takes energy to fabricate the car, and it takes energy to mine the minerals that we use to fabricate it. So I gotta mine iron and make steel, build a car. You're right.
So I mean, just so that we can account for electric cars as well.
Right. Yeah. Good point. And we will take that into account later in the course. Yes. So I was ready for that one. But you know what? This is too hard. I'm going to measure the energy used here at the car because it's very straightforward. And later on, we'll take a look at all these other things and see how they factor into it. But just in terms of how much energy do I use in my car, I'm going to use this. We'll include those other things in some other part of our analysis. So this is just saying the same thing. Oh, I forgot to show the distance guys the screen, so they had no idea. Oh, well, they can see this PowerPoint. So we should measure at any point. We need to be fair, and we need to measure the production at the same point. So measuring at point of use is good just because it's easier to compare with different technologies, and it's easier for us to do. See below. What could be below? Oh, here's an analysis. So to figure out how much energy we use per car measured at the car, we know this problem involves intensity, distance per day. The average American drives something like 12,000 miles per year. And I think this number is the same for British, which was surprising to me. Then it also involves intensity, it involves efficiency, which would be miles per gallon or some kind of unit like that. And then it will involve the energy density, how much fuel per unit hunk of energy, fuel. So here we have 12,000 miles per year, and I want to get kilowatt hours per day. So I'm going to convert years to days. So 1 year equals 365 days, so I can cancel the years. I want to convert miles per gallon. Well, this is 1 over efficiency, so gallons per mile. Let's say my car gets 28 miles to the gallon, so gallons over miles. I got to convert that to liters per gallon, because I know the energy density of oil is about 10 kilowatt hours per liter. If I multiply all that stuff together, blah, 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 I get something like 40 kilowatt hours per day per person. Well, per car. We said the average car is driven 12,000 miles. Exactly, if you crunch the numbers, it's 43. But, you know, we just want to get a handle on the numbers, so we're just going to use these approximations. 40 is close enough for the purposes we're doing. This is not ultra precise. So the energy used per day is the distance traveled per day over the distance per unit of fuel times the energy per unit of fuel. And I probably have some little canceling units, so I canceled miles here, canceled years, canceled gallons, canceled liters, and then I ended up with kilowatt hours per day. This does not include, as we said a moment ago, the energy used to produce the fuel, and that long chain of energy waste used fuel, the energy to produce the car, as you pointed out, the energy to ship the car from Japan to Columbus, we forgot about that. Oh, and there's the energy to build the road, so all of that stuff is not included. It's just in my magic card. All right, so that, we said 12,000 miles per year per car, and then we're basically assuming one person per car. Is that really fair? Here's the consumption stack, 40 kilowatt hours per day. What do you think? Should I just assume pretty much most of the time one person per car? Or should I assume that most of the time cars have other people in them? Any opinions? When you drive down the road, what's your observation? Most of the cars have one person or multiple people? We don't know. We all walk to school. Huh?
Usually one.
Yeah, usually one. It's funny you should say that. Here's how many Americans drive to work. This blue thing is drive alone. You can't read that from where you are. This red thing is carpooled. The green one is the bus. There's a few little extras. This is a streetcar here, this little sliver, subway, railroad. This one is taxi. This is bicycle, walked. So you guys, most of you walked to school at least the first day of class. Other means worked from home. Far and away, we mostly drive alone. It's about 3/4. So we could take the 3/4 of that 40 kilowatt hours a day, or 40 kilowatt hours a day, make it 3 kilowatt hours. I'm going to say 40 is probably good enough. Let's compare us to Britain. This is Britain in 2001. This is the United States very recently. Britain driving in a car, 55%. Passenger in a car, 6%. Bus or coach, oh that's so ethnic, 7%. Train or tram, they have to translate these English words into American. 7%. Bicycle, 2%. On foot, 10%. On foot, 10%. Walk, 3% for us. Working mainly at home, 10%. For us, 4%. Interesting. So just to compare their lifestyle with ours. Also, I thought it would be interesting to compare 2009 data, which we just showed, to 2005 data. Driving alone, 77%. Driving alone, 76%. Tiny decrease. Carpool, 10%. Carpool, 10%. Actually, this is closer to 11. That didn't change very much. They added motorcycle in this one. So there really hasn't been much change in our lifestyle over the last however many years. Just curious. So this business about 75% of people driving in car or getting around just driving alone. So we should account for that. Now, this stuff doesn't involve cars. We have drive alone and carpooling, and then the rest are alternate transportation. So it'd be closer to maybe 80–85% would be cars. So we could multiply by 75 or 85% to get something smaller, but we're going to account for these other modes of transportation in later chapters. I'm just going to let it stand for now for simplicity. So we're going to say 40 kilowatt hours per day. Okay, so that's the stack. This is our first entry in the stack, energy consumption. This was 40 kilowatt hours today for the average Brit, and I'm saying it's roughly the same for us. Which actually surprised me. I would have thought we drove more because we have less public transportation. Maybe that's my imagination. We don't care about that. So now we have a consumption. Let's look at a production. Let's look at wind power. How much wind energy could we produce? Just one possible source, and we're going to look at them all and see if any of them will save the world. All right, so let's take a poll. The UK, so here's a map of wind intensity in Britain. And the darker the green, the more intense the wind. I'm guessing there's like mountains here, or, well, maybe tall hills, something like that. There's some areas up here that have some red. Red is bigger than 10. I'm sorry, darker green is less. I lied. Darker green is less. So this color is less than 5 meters per second. And it says at 25 meters above ground level. Why would they measure the wind up there? That's where the windmills are. Yes, that's right. So this is less than 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10, and greater than 10. So the UK has good wind in what percent of the country? So how many people would say 10%? Okay, one. How many people say about half of the country has good wind power? Nobody's saying. How many people think most of the country has good wind? Okay? I'm going to claim it's less than 10%, depending on how you define wind, because most of this is these green areas, which are the lower wind speeds. Here's daily averages in Cambridge. Speed in meters per second, this is 2, 4, 6. So they get a lot of wind in the 2 to 4 meters per second range. And this is half-hourly averages. Here's 0. Most of the time the wind is still, and it dies off. They don't get high winds very often, at least not in Cambridge. Who knows where Cambridge is? Yeah, me either. I was going to point to it, but I don't actually know for sure where it is. So he's saying, the author, that these are the regions that have better wind. There's a little bit more wind in these general areas. And so that's where you'd put windmills if you were going to put them. Okay? Now, those windmills that they use, they don't produce any energy below 4 meters per second is what's crossed out here. So all of this time, which is most of the time, those windmills can't even turn. It takes at least 4 meters per second of wind to turn them. So they have very little wind energy. Doesn't mean they shouldn't use it, just saying, you know, it's not Kansas. From the book, Class 2, that's defined by the National something energy something, we use it here too. Their wind power is on the average of 2 watts per meter squared. 2 watts per meter squared of land. So the windmill is on a piece of land, and for every 2 square meters of land, they might get 2 watts. Okay? This is just making clear it's not the area of the rotor, it's the area that this thing's sitting on. England has about 4,000 square meters per person. Yes?
When you say it's the area it sits on, are you talking about just the base or including the wingspan of the windmill?
Actually, what I'm including is, if I had a windmill farm, there's a limit to how close I can put the windmills together.
So the whole farm.
So the whole farm, right.
Okay.
So it takes into account that there's space between them. Thank you for that excellent question. England has 4,000 square meters per person, and you can't cover all of the land with windmills because you have to put up schools and grocery stores. So he's saying, suppose 10% of the land is covered in windmills, you might want to use some of the land for other things, like living on. Then 2 watts per square meter times 4,000 meters per square person times 10% of the land, and of course, this would be concentrated in those areas that we circled before. These are unit conversions because we have watts over here. We want to get kilowatts, so we have kilowatts over watts. Hours per day gives me 20 kilowatt hours per day. England could reasonably expect to generate something like 20 kilowatt hours per day per person. The per person didn't make it over into here, but it should have. If we figure they're using their existing wind, how much wind they have, and peppering 1/10 of their land area, 10% of their total land area with windmills. And that doesn't include transmission losses. They're fairly small, so this is power more or less at the point of use. Because this is, remember, this 2 watts per square meter is measured where the windmills are. Then you got to transmit it. But if you're transmitting over high voltage transmission lines, it's not terrible. If this says transmission losses in the U.S. are estimated about 7.2%. Yes?
What was the average kilowatt hour per day for one person to use? Didn't we
40.
Do that recently?
For a car?
No, just for a person.
No, I don't think we've calculated that yet.
Yeah? Okay.
No. I think we're working our way up to that through this course.
Okay.
Yeah. And you'll have plenty of opportunities to try to put these numbers in perspective, which I can tell is what you're trying to do. Like, is that a big number? Is that a small number? That's exactly what we're trying to figure out in this class. So stay tuned. All right. So we neglected transmission losses, and of course we neglected somebody has to build the windmill and they have to mine whatever the windmill's made out of. But still, here's wind in the UK. This is a style of windmill that evidently they use there. Quiet Revolution brand. This is kind of cool. It doesn't look like ours at all. So these vanes rotate, And at 5.5 meters per second wind speed, this generates about 6 kilowatts. And you have to space them at least 10 meters apart. Okay, so that's where that 2 watts per square meter came from. So consumption for cars, kilowatt hours per day per person, 40. And you could generate with wind, with fairly optimistic assumptions, 20 kilowatt hours per day per person. It's going to take more than wind. This is more about the wind speed. It has to be above a minimum speed to turn the gears. That's true in ours as well. If wind has to be below some maximum speed. So these, I don't know about theirs, but well, there's the blades, I guess, lock. In ours, they can feather the blades. So if the wind is really, really strong, they can aim the edges into the wind so there's less force on the windmill and doesn't damage it. So the quiet revolution one that we just saw has a range from about 4.5 meters per second to about 16 meters per second. So most of the time in Cambridge, here, this is 4. The wind isn't useful. It just isn't even strong enough to get the windmill started. At least in Cambridge. But I'm guessing there's windier places in Cambridge. Now here's an interesting fact. Windmill power increases as the cube of the wind velocity. This is huge. So if you double the wind velocity from 4 to 8, you actually will cube the power that you get out. C is some constant, and we'll give you a homework problem. You're going to know what the power is at some wind velocity, and by doing that you can calculate C. And then after that you can try different velocities and you can see what the power is. So if your wind speed doubles, your power output increases by a factor of 8. That's a big deal. In engineering speak, that is like totally cool. So we definitely would benefit from putting windmills in really windy places. The windier the better, as long as it's not so windy it destroys the windmill. Places like Cambridge and maybe Columbus, maybe not as useful just because our wind powers are so low. In 2010, the last time I taught this class, Ohio had 2 wind farms. One wasn't even a farm. They had 4 windmills in Bowling Green. They produced a total of 7.2 megawatts nameplate capacity. So you'll see this term a lot when you're looking up about nameplate capacity means under ideal conditions, how much would this windmill produce? Nameplate, so that's the max basically. But it's never ideal or rarely ideal conditions, so most of the time they're producing less than that, just to give you an idea. The average wind power density up in Bowling Green is about 250 watts per square meter at 50 meters up. That sounds huge. That's got to be a typo, because the previous slide we saw for England it was 2 watts per square meter. I don't believe this number, so look it up and see what it should be. But the average energy production for that 4-turbine farm was 14 megawatt hours. And then the other one was a single Vesta, this is a Vesta brand windmill, was at the Science Center up in Cleveland, and it was mostly for show. Well, they do produce some energy, and it's still there. Then somebody decided to invest in wind energy in a major way over the last couple of years, and in 2000, actually, Ohio's adding wind faster than any other state in the nation. Vermont is second, I'm happy to say, since I'm from Vermont. And we increased our wind capability by 900% in 2000 alone. This comes from Dayton Business Journal. And if you've ever driven along Route 30 up near Van Wert, it's all windmills. So that in one county, and when you get to the county line, boom, it stops abruptly. But they added a bazillion of these things. We're number 13 in the country in total wind power production. Number 13 in the country, and we're not Kansas with lots of wind. We're not Texas with lots of area. We're just Ohio. So we're doing a good job here. We put up 210 turbines near Van Wert. This is Van Wert right there. In 2011, 210 new turbines at 1.8 megawatts. So these are big, big turbines. Give you an idea, here's one of the blades. Here's a person, standing, a cute person there, an adult person. Here is the propellers laying on the ground. Here is the stock they stand on, and these are houses or trucks or something large. Just to give you, have you seen these blades going down the highway? Yeah, they're big.
I think OSU just purchased an amount
Yes, I'm going to talk about that in a sec. You are absolutely right. So currently we have about 1,000 megawatts built or under construction, and we have 775 megawatts more proposed. So we're nearly going to double what we have. These are the locations where those wind farms are. Green ones are operating, so here's Van Wert, and here's something called AMP Ohio, and here's the Great Lake Science Center. Under construction are yellow, and you can see a bunch of them here. Purple is proposed, like Black Fork, and this color here is canceled or decommissioned. That one there is the only one I see in that category. So we increased our capacity by almost 1,000%, and we're going to double that nearly in the next year or two. So why is it all in Northwest Ohio? What do we have wind resource-wise? Here is a map of the wind resources in Ohio, just like the one we saw for England, only the color code is different. White means no wind. Brown, I can't read this, but it's light wind, and it's in the same ballpark as the Cambridge wind. Yellow is a little bit harder, and then pink, purple, and red. So if you were going to build windmills in Ohio, where would you build them?
In the lake.
In a lake, an excellent answer. We're going to talk about that in a sec. But if restricting yourself to land, you'd be up in this area. And there'd be no point for OSU. OSU wants wind. No point for us to build windmills in Columbus, although there is one at the Bayer car dealership, and I can talk about that at some point. Average wind speed near Van Wert is about 6 miles per hour. And to give you an idea, to compare with the Cambridge numbers, that's about 2.5 meters per second. So that's under the range where the windmills in England worked. So Ohio is also class 2 in places. Class 2 was 2 watts per square meter. So let's say maybe a third of Ohio is class 2. Does that look fair to you? The brownish area? Okay, so this is an engineering approximation. So it's comparable to Cambridge in terms of wind energy. About 2 watts per square meter of ground area can be harnessed. Let's suppose we cover 10% of that area, because we have to leave room for cows and restaurants. Cover 10% of the area with windmill. How much energy per person per day could we generate in Ohio? The area of Ohio is 41,000 square miles. We have 11.5 million people in Ohio. So the procedure for doing a calculation is we'd say, well, how much area? A third of the area we're going to populate with windmills gives me about 35 giga square miles. No, not giga. What? This is another mistake. Oh, meters. Oh, meters squared. I did a conversion there I didn't show. Scared myself. And then 10% of that, right, because we're only going to cover 10% of the area, leave room for other stuff, is 3.5 giga square meters. The power is 2 watts per square meter. If I multiply that by the 3.5 giga square meters, I get 7 gigawatts. And if I divide that by the number of people in Ohio, because we all want to share the wind energy coming from Van Wert, we get about 0.6 kilowatts per person, kilowatts per person, and then I convert that to kilowatt hours per day. 14 kilowatt hours per day per person in Ohio if we populate 10% of that upper northwestern third of Ohio with windmills at that capacity. So this is the result for Ohio so far. I say we're about 40 kilowatt hours. You could say 30. We need to fix this. This is going from 30 to 40. It should be 0 to 40. So we could even say it was 30 because of that 75% calculation. We decided to ignore it. And our wind is maybe 14. So we also are going to need something besides wind to satisfy our energy use. But I heard someone say, Lake Erie. That's where the wind is. And people are really looking hungrily at Lake Erie. It has a lot of advantages. One is it's purple. So there's a lot of wind out there. There's no obstacles, right? You don't have to worry about cows and restaurants and things. There's lots of wind. The lake turns out to be shallow. So unlike Lake Superior or something, Lake Erie is fairly shallow. That means that installation of these things would be comparatively easy. You still have to go out in the water, but it's not as bad as someplace really deep. The average depth is just 62 feet. Well, that sounds manageable. But it's still more expensive to install wind than on land. But you know, if you can overcome the initial investment, you're going to get a boatload more energy because again, the power goes as the cube of the wind velocity. So that's a huge, huge advantage. And another advantage we have in Ohio, how often do you get to say advantage in Ohio? We're deep inland. Those pesky hurricanes can't get to us in here. So Lake Erie is a safe place. We don't have to worry so much about damage from the weather. We also don't have earthquake, well, not big earthquakes. And the turbines can feather their blades, that means rotate them into the wind, and they even have brakes if the wind gets too strong. So we could put windmills in Lake Erie and reap a boatload of energy if we could figure out a way to afford it. So I think that's and a lot of people are proposing that. I haven't seen anything more than talk. I haven't seen anyone say, yeah, we have funding and we're going to do that, but people do talk about it quite a bit.
Who has rights over the lakes? Do you have like Michigan bordering it and Pennsylvania bordering it? Like, do you have any idea how that would be?
No, I don't. And sometime later in the course, I'm going to give you a problem where we're going to compute how much wind energy could we get from Lake Erie. And the first thing I did was I looked at a map and I said, okay, how much of this lake do I say belongs to Ohio? How much to Pennsylvania? How much to Canada? And then I just took our part that when I did that problem. Does it touch Michigan? It does, doesn't it? Right up here.
Touches a lot of
Michigan?
A lot of states.
They can't have our wind. If you were the United States and not just Ohio, where would you like to put wind?
Oregon, California.
Yeah, along the coasts, right? That if you could afford it. Now, putting wind on the ocean is harder. The salt environment will eat metal and corrode things, so that's bad. But there sure is a lot of wind. It's hard to put things in the ocean because it's deep and it's sloping and sharks will bite you. Maybe not sharks. They do have hurricanes, especially over here. So that could be a problem for those guys. Suppose you were just going to put them on land. Oklahoma, Kansas, even the Dakotas. Even, what's this? Let's see. Wisconsin, Minnesota, right? I don't think of Minnesota as windy, but I guess it is. Arizona, New Mexico. Sorry, Arizona, New Mexico, not so much. Coasts are good. This color scheme I can read. This is brown says marginal. That was Ohio. Yellow is fair. Pink is good. Purple excellent. Red is outstanding, and this color blue is superb. I bet it's expensive to put windmills out there, but yes.
For the California coast?
Yeah.
What kind of issue are earthquakes? Like, would they just topple over and like, or do we know at all?
I don't know.
Because I would assume like a tornado would just absolutely destroy.
I would think that if you were going to build windmills in this part of the country, you would have to have a way to make them tornado-proof.
Yeah.
Like feathering I'm thinking of just putting brakes on wouldn't be enough. I think you'd have to feather those. Wow, but then you have to know what direction the wind's coming from.
Yeah.
Oh, an interesting engineering problem. But I'll get back to you in a sec. But to answer your earthquake, I think the problem with earthquakes is what are they standing on? Are they bolted to the bedrock, which I think they'd have to be because they have to push against something in order to turn the rotors.
I mean, they can make buildings that have structures that are earthquake resistant.
Yeah, but I'm just thinking like a windmill because it's more.
Yeah.
I know what you mean.
Yeah.
Now. I was just wondering if like that might be something besides the fact that it's like an eyesore that's preventing it from being on the coast. Not that
I think it's probably more the investment issue. The eyesore issue is one, but a soft coast is not as big a deal. But those buildings that can flex. The way that they work is that they absorb energy from the earthquake and they flex to dissipate that energy so it isn't used to crack the building. If you do that in a windmill, then when on a normal operation, the thing's going to flex and you won't retrieve as much of the energy.
I mean, the earthquake won't be like a super long-lasting situation, though. You know what I mean?
True, but if the windmill is made flexible so it can sustain it, Then when the wind
I
blows
get what
on
you're
it, a lot of that energy is going to go into deforming the windmill. What were you going to say?
Could we make it so that the windmill lies down when it comes?
I don't know. That's an excellent idea. I like that one. He said, could we make it so that the windmill, the whole thing could just lie down when the wind is strong?
Make sure there's no cows under it.
Well, out in the ocean. I'm not
Yeah, I
too worried.
suppose in the ocean.
Yeah, there's very few
Going
cows.
for tornadoes.
Take a nap.
Tornadoes. Oh yeah, so you're saying in this area, if you can make
Yeah.
them so they could lie down?
I feel like our ability to predict tornadoes versus how much time and energy it would take to lower those wouldn't be like efficient. And, you know what I
Yeah,
mean?
take an hour to lower the thing.
Yeah, and we probably know a tornado's coming. Like, do we even know for sure?
Well, they have tornado watches and
Yeah, but I don't know.
warnings.
But then if it doesn't happen and you just spent all that time, and I mean, it's got to take a ton of energy to lower that giant windmill. I feel like it wouldn't.
I don't know if so I'm thinking this is a creative idea, so I'm kind of interested in exploring it. The post probably isn't a big deal because it doesn't have a big cross section. But if there was a way to, yeah, suck in the vein, you know, and just put them in the middle. I don't know. I think that's an interesting idea. Okay, so here's the United States. Coasts. Ohio State University, someone was mentioning. So we have committed to buy 50 megawatts of energy from the Blue Creek Wind Farm. Blue Creek is orange. That means it's under construction. Okay, so it doesn't exist yet. They're saying it would supply campus with about 25% of the total energy need for campus. This is the Columbus campus, we get that. However, we will have to use transmission lines to get the energy from there to here, yes?
You know what the cost difference is?
No.
I was talking to the person who was in charge of purchasing it, and they said it's actually going to cost them less to purchase the wind energy. They were able to negotiate it somehow.
It's going to cost them less to purchase this wind energy than what?
Then from AEP.
No fooling.
Yeah.
That's awesome.
That's surprising.
There's hope for us.
I'm sure it has something to do with subsidies.
It must
Oh,
have something to do with because again, these guys are being subsidized in a big way, which is a good thing, I think, because I want to have wind power.
Do you know how that works? Because we buy bulk, natural gas, and we do that at our own plant, and then we just buy credits for the wind energy up there, right? Because like they don't actually take the energy from all the way up there down to Ohio State.
No, I thought they were going to actually use transmission lines to bring that energy to here. I don't think it's a credit substitution. Is it?
I don't know.
I don't
Make
know.
more
What an
sense.
excellent homework
Credits.
problem.
Yeah, I don't know.
Homework 2, find out.
Pretty sure. I assume it's just an energy credit. 'Cause I don't.
I would be disappointed if that were true. The article that I saw, which I didn't cite here, said that we were buying the energy from the farm. Huh.
It would make more sense with credits, since the infrastructure already exists.
So this person that you know is buying the, can you ask him? Find out? Okay.
Yeah, absolutely.
Creek, and I'll put my crack team of investigators on that also. But I'm excited about this. Okay, so we got cars and wind. Now let's talk about planes. Let's do a poll. Anybody fly the past year? 3 people, 4 people. How many of you flew a domestic flight? All of you. How many people flew internationally? 2 of you. So you had multiple flights then, unless you're counting flying to Chicago to fly out. Which is closer by air, China or India?
For us?
Yeah,
Oh, from
Ohio.
I don't know.
I don't either. I knew when I wrote this. I looked it up, but now I don't remember. I hope it's in here somewhere. I guess it must have been India. So let's say you take 1 intercontinental flight per year. That appears to not be a reasonable assumption for this group. This group, only half of us flew at all in the past year. But last time I taught this, I had a classroom full of Chinese students, so for them, it's more realistic. Take a nice, comfy Boeing 747. It has 240,000 liters of fuel at liftoff, so it has to carry all that weight. If the plane is full, it's about 416 passengers, and if they're American, they're obese. They can go 8,800 miles on a tank of gas, about 14,000 kilometers. A little further than Columbus to Delhi. Oh, it can go a little bit further than from Columbus to Delhi, but there isn't a direct flight either, so we'll call it a wash. To get there from Columbus, you have to go land somewhere and transfer to another plane. And let's say you take one round trip per year. You go home and visit mom in India once a year. Then the energy used per day, so one full Boeing 747 making a round trip of 8,800 miles each way, using full tank of fuel. I have round trip, 240,000 liters, 416 passengers to get per people. The energy density of fuel, we're using 10 because it's a round number, gives me 11 point something kilowatt hours per passenger, or about 12 kilowatt hours per passenger. We'll call it. If you do it once a year, then per day it works out to 33 kilowatt hours per day per person. That one flight to visit mom in Delhi cost me more than driving my car, well, about the same, a little bit less, than driving my car 12,000 miles a year. Wow. Quick. Probably we don't all take a international trip, so we rounded it down.
That's just one direction?
No, that's round trip. That was round trip. But once per year. So that's a little sleight of hand because it's a pretty long trip, probably longer than most of us take. We used 8,800 miles because that's how far the Boeing 747 could go. If you think London to Cape Town, that's closer to 10,000 round trip, so let's use that. Blah, 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 crunch the numbers, 23 kilowatt hours per day. So this is David McKay in London. He's going to fly to Cape Town. But he thinks, because he lives in a fantasy world, that a plane may only be 80% full. That was true when he wrote his book. Has anyone ever seen a plane that's only 80% full? Not in my lifetime, not lately. Anyway, so if that's true, we can get something like 30 kilowatt hours per day.
I've made that trip. It's long.
From London to Cape Town?
Yeah. It was forever long.
I'll bet. But at least when you go south, you don't have the jet lag problem.
Right.
Yeah. Let's try a more efficient plane. Let's try the new Dreamliner. We need, again, to know how far we travel, how many people, fuel efficiency, and fuel energy. So the Dreamliner claims to be 20% more fuel efficient. So that would give me 13,000 gallons and a 3,500 mile-gallon range, 4 gallons per mile. Airplanes don't come in miles per gallon, they come in gallons per mile. So do tanks, come in gallons per mile. 12,000 miles per year, 4 round trip. This is 4 round trips from Denver to New York City, or 1 round trip Denver to Europe. Why Denver? Because the person who taught this class before me, she gave me all her slides, she's from Denver. So use the same method for the car calculation. We have miles per year, years per day, gallons per mile, liters per gallon, kilowatts per liter, blah, 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 5,000 kilowatt hours per day. And what's missing here is the per person. That's for the whole plane. So the Dreamliner carries 300 passengers. We'll call it 250. So per person, it's about 20 kilowatt hours a day. Trip to Frankfurt would be a half of 12K in one day. That's about half of 20 kilowatt hours per day times that blah, blah, blah. 3,500 kilowatt hours per person in a single day. But of course, you don't fly it every day. So you have to amortize that over the whole year. Frequent flyer, maybe do that 2 or 3 times, so maybe 40 to 60 kilowatt hours per day if you do a lot of flying, traveling. So there's a lot of variability. People travel different amounts. It also depends where you're going. Taking off and landing are cost intensive, energy intensive, so planes are more full this day. Your mileage may vary, don't get out much. So it'd be fun to develop your own stack. You might think, well, how much do I personally fly? Well, I'm going to ride my motorcycle. So this is a picture of my old motorcycle. It's a Honda Pacific Coast, or at least it was. It's 645 pounds, so it's a lot lighter than a car. Number of passengers is 1. Mileage commuting is about 45 miles per gallon. It's a pretty heavy bike, but it's lighter than a car. It's about a 30-mile commute round trip for me, so I figured out that results in about 0.5 kilowatt hours per kilometer that I ride my motorcycle, and 24 kilowatt hours per day each day that I commute, but I can't commute all year long because of ice and snow, and I'm a wimp. So maybe 16 kilowatt hours per day averaged over the whole year. Let's compare different kinds of transportation. A car has 1 passenger. This column here is kilowatt hours per 100 people kilometers. So for every 1 person that has to move 100 kilometers, how many kilowatt hours is it? Car, 80. My motorcycle, 45. Van pool, 25. Because you're going dragging the car, but you got several people in it, 6 people. Going by air, 50. Intercity train, 10. Trains turn out to be remarkably, surprisingly efficient. We're going to look at trains later in the semester also. Just to give you an idea. So what's the best way to get to work?
Walk.
Walk, right. Trick question. All right, so to summarize where we are so far, we're going to measure the energy use and creation at the point of use, so at the gas pump or whatever. Car travel is a big chunk of our energy budget. So if we were going to look at ways to reduce our energy consumption, this would be the first place to look, in my view. Wind has a small contribution in the UK, negligible in Ohio at present. This is from the last time I taught this course. I'm not sure if it's negligible now. We'll take a look at that. We'll see some charts. And in planes, although infrequent, they're energy intense. So better than cars on a per person basis, depending on how much you travel. So we still have time. So I think I'm going to go ahead and move on into the next part of the lecture. So far the consumption stack is winning. Egad, transportation, more transportation, wind. Oh, we need more energy. What should we do next? Solar energy, it says right there.
It's not great for Ohio either.
Yeah, no, solar's not great for Ohio, but let's take a look. Where would a solar panel work best? North Pole, London, Columbus, or the South Pole? How many people think of the North Pole because the sun shines there 24 hours a day, half the year? Nobody's falling for that one. How about London? Is London better than Columbus or worse?
Worse.
Worse. How about the South Pole? That's really sunny because south is always sunnier. No, you guys are too smart. Yeah, location is everything. And here's the reason. So the latitude affects your irradiance. If let's say the sun is high noon at whatever the summer equinox or solstice, whatever it is it's called, the sun is coming right overhead, then you're collecting all the rays. If you live in London, even on the best day of the year, you're getting what we call in engineering the cosine projection, which just means this is slanted. So those rays, I have the ray space the same way here, and the length of this green thing's the same, but when I tilt it, I'm only capturing 3 of the rays instead of 5. The farther I tip that guy over, the farther north or south that I go, the less sunlight I actually get. Cambridge is at 52 north, Columbus is at 40 north. So we're closer to the equator. We don't get to say that very often either. So we're actually going to be in a better position solar-wise than London. Here's the sun. Here's the energy from the sun. Solar radiation at the equator, at the equinox, outside the atmosphere, like where the space station is, 1350 watts per square centimeter. Or square meter, square meter. That's pretty. Compare that to how much wind energy we could get 2 watts per square meter. So that's pretty good. If you live in Djibouti, close to the equator, that's very good. Except for that's inside the atmosphere. So at the Earth's surface, due to atmospheric absorption, we get down to about 1,000 watts per square meter. Oh wait, it's dark at night. Chop that in half. 500. Oh wait, the angle varies over the day. because it's not noon all the time. Chops it down another 320. Oh wait, the Earth wobbles, doesn't wobble. As the Earth is, here's the sun, the Earth rotates like this, so your cosine projection is changing, so you get some variation, plus or minus 23 degrees. So 300 is basically the best we can hope for at the equator, even. Specific locations are less. So London, these are numbers that were actually, these numbers are the best we can hope for based on our cosine projection, our angle, and all these other factors. So Columbus, cosine of 40 is 0.77, cosine of 52 is 0.62, Djibouti 0.97, so they're close to 1, so they have the highest. So Columbus, best we could ever hope for, 2:30 at noon, summer solstice, all that. 180 for London and almost 300 for Djibouti. London is famous for fog. Columbus is, well, we have pollution and clouds too. So what we actually measure is 140 in Columbus, 110 for London, 270 for Djibouti. Let's go there and get their energy. So we're down from 1350, almost 1400, to 140. So we lost 90% of the sun just going through the atmosphere and coming to Columbus. Now there's different kinds of solar power, and we won't have time to talk about them all today, but here's some potential things we can talk about. There's heat, solar thermal, using the sun to heat something up and using that heat energy for something. Another way is to use solar photovoltaics to produce electricity. So photo means light, voltaic, electric, so photoelectric, as opposed to this, which is heating water. I'm going to make a clear distinction between those.
Or liquid.
Huh?
Or liquid.
Or liquid, or air. You're right. It could be other things. And you can heat the inside of your car and sit in there and warm up. Biomass. This is a type of solar power in the sense that the bio stuff needs the sun to grow. It grows, it gets energy from the sun, converts it to sugars and starches and apples, and then it makes fuel. And you eat the fuel, or you burn it, or you do something and retrieve some fraction of the energy. And food is good. And we'll start with solar thermal. So the idea here is you're going to use the sun to directly heat something, and then you're going to use the heat energy. Notice there's no electricity in this version. So one idea would be you could put flats of water on a south-facing roof. I have a story to tell you. Time out. When I was in Brazil, no, that wasn't when I was in Brazil. But my dad had a friend in Brazil. That's the way the story goes. Dad had a friend in Brazil who wanted to put solar energy on his house. This was back in the 1960s, no kidding. And so it was because, Brazil, what an awesome place. It's hot, it's near the equator. And so he read all the literature about solar panels, and they all said, put these solar panels on the south side of your house. No fool, and he did. The guy was an engineer, and he put them all on the south side of his house. So he's at the Tropic of Capricorn. That didn't work out so well. But anyways, let's say we're in the northern hemisphere. Put flats of water on a south-facing roof. You let the sun heat up the water, so that generates heat. Again, I'm going to emphasize not electricity. Photovoltaics will do that. But you can use the heat for heating, right? You cannot use heat to charge your cell phone. So or run your TV, so we call it low-grade energy. You can use the heat to create electricity if you wanted to use the heat to boil something, there's transition losses there, and use the steam to crank something, there's losses there, and then use the crank something to generate electricity, remember all those losses? It'd be nuts to use heat to create electricity in this scenario. It's nuts to do it even burning coal, but that's the only way we can do it. So this is low-grade energy, but it does work for heating your house, heating your bath water potentially. So we're going to take a look at how much solar thermal energy could we realistically get and what could we use it for. Here you see the solar collector, there's hot water goes down here, it goes through here, exchanges the heat with this tank of cold water, and the heat heats up this water which goes into a boiler or to the taps or whatever. So let's see, solar thermal. So this is the UK numbers. He says the area per person, that's the area of the panel that you're going to aim at the sun, that you're going to heat up. The solar power per area, we know that number was 110 watts per square meter for London, times the efficiency, and that's going to give us power per person. So he says, well, his roof, about 10 meters square per person. So he's taking the size of his roof and how many people live in his house and coming up with area per person. Of course, you can only use the south-facing side if your roof's slanted. Times his energy density there, and let's be wildly optimistic and say 50% conversion. So 50% of that solar energy actually gets converted to thermal energy and only half is lost. And if you crank out the numbers, blah, 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 he gets 13 kilowatt hours per day per person. So I thought, well, what about my house? So I have at my house, I live in a typical suburban house in the United States. 10 meters per square per person is low. My house has about 80 square meters of roof, and if there's 4 people living in my house, that's 20 meters squared per person. So I think this would be a more typical number for Ohio, let's say. 50% efficiency is generous. Much heat is wasted in the summer because everything's already hot, so you're only increasing, the change in temperature isn't as great. Columbus is better than the UK, slightly, 140 versus 110. And for my house, my numbers were more like 33 kilowatt hours per day per person. You can do it for your house. Now, how much energy is that? What can I use this for? Let's say I was going to use to heat my water, okay? So if the water enters the house at 5 degrees Celsius, because it comes from pipes underneath the ground, so it's pretty cold, and let's say my solar thermal heats it to 40 degrees, and let's say I use 5,000 gallons a month, and half of that is hot water. So some of it's cold water, some is half, and let's say there's 4 people in my house drinking the water and taking baths. Then I run these numbers, blah, 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 blah. This is the change in temperature. I had to increase the temperature from 5 to 40. Blah, 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 blah. 3 kilowatt hours per day per person. So an estimate, and I'll make the distinction here between an estimate and a guess. An estimate is based on some numbers, like this. Okay, they're not exact numbers, but we have some general idea. We have some basis for choosing these numbers, and we can run that through and we get an estimate. A guess would be, oh, I don't know, 3? Without any basis. So this is an estimate. 3 kilowatt hours per day per person of hot water that I might use in my house. Now, the solar heating, you could go nuts and put lots of solar thermal panels on the house. So here's the south side of a house, and I'm thinking that these are probably photovoltaic, but I can't tell for sure. These are solar thermal heating up water things. These are windows that give a greenhouse effect, I think. I think I have these labeled here. Yeah, so this is water, and this is water, and these are windows. So they're using this to heat the house, right? The greenhouse effect. It's still solar thermal heating. It will still work in winter. Will it be enough in winter to heat up that house? I don't think so. But it helps. So you could go nuts and put lots of solar thermal panels on there. Hot water and hot air. So suppose you can cover 10 square meters per person with solar thermal, and still 50% heating efficiency, or efficiency converting sunlight into heat, using England's number for 110 watts, cranking the numbers, 500 watts, convert to kilowatt hours per day. Basically, the result was 13 kilowatt hours per day per person, reasonable estimate of solar energy in Cambridge. I'm getting depressed. These are, well, this could vary, right? This is pretty typical. Optimistic wind, pretty aggressive solar heating. Is that realistic? 50% efficiency is pretty darn good. Here's a commercial unit I found, the Viridian unit. Did I find this, or did McKay? I don't remember. It's got an area of 3 square meters. It produced 3.8 kilowatts per day at European latitude. Average power per unit area is 53 watts per square meter. And incoming is 110 for that latitude, sorry. So actually 53% is not unreasonable. I thought that was pretty optimistic. Solar thermal, pure thermal power again is less useful than other types. So it's not as useful in warm times of year. It's tricky to store heat. That's another problem. You'd like to have energy available whenever you want it, not just when the sun is out there. You can store electricity in batteries. That's a whole other issue. Don't get us engineers started on batteries. We'll talk about that another day. But we can't store this because it's not electricity. How can we store heat?
Thermos.
A thermos?
Really, really big thermos.
So you need a big thermos. So you're thinking something big that's well insulated. You put hot water in there, and if it's well insulated, the heat energy can't leak away very quickly.
Right.
Is that your train of thought here?
Yeah.
I'm not trying to put words in your mouth. Yeah. So people have been talking about storing thermal energy by pumping the water into holes drilled in giant rocks underneath your house. And the idea is a rock has a high thermal mass, so it's hard to heat it up, but then it's hard for it to release the heat. So it won't leak too bad. It's a big thermal mass because you have a lot of energy you want to store. Does that sound practical to you? Maybe. I don't know. We don't have it yet. So it's tricky to store. I can store hot water in a giant thermos, like you just said. 1,000 liters a day, maybe. I don't know. Can't transport that. So if I generate the heat at my house and then I want to use my cell phone at work, no, that's not going to work. I can't transfer that energy I made at my house to my car or anything like that. Can't power the lights or computer. So thermal energy is low-grade energy. This is really important to keep in mind. Electricity is really good kind of energy. There's trade-offs there too because how efficient is it to make it. But thermal energy does have uses. If it's heating you want to do, and if it's heating here where the heat is coming from the sun, then this is definitely a viable option. And I think this is a great place to stop. Next time we'll talk about photovoltaics and biomass and more like that. So, are there any questions?
So we're going to talk about thermal energy on a macro scale.
Are we going to talk about thermal energy on a macro scale? Are you talking about geothermal energy?
No.
That kind of macro? What are you talking about?
Like CSPs.
What's a CSP?
Concentrated solar power.
Ah, yes. We'll talk about concentrated solar power.
Because we just talked about it on kind of a micro scale.
Yeah, and I'm going to talk about concentrated, like solar farms.
Oh.
Okay, is that what you're hoping
Yep.
for? Okay, great. All right. Hey, no class on Monday.
Oh, that's right.
Try not to be sad.
What are the next chapters to read?
I don't need. The question is, what are the next chapters? I don't remember the chapter numbers, but the next things we're going to talk about are solar photovoltaic. And you know what? I don't even remember what comes after that. But I would read the next couple of chapters.
What chapters were we up to today?
I don't remember that either. 4? Yeah, they're short chapters. So do you guys feel like this book is fun to read?
Yeah.
I think so. All right.
You guys have any questions yet?
I'm not.